Today we're going to explore one of the most remarkable discoveries in physics, superconductivity. This story will serve as an experimental guide for young researchers on how unexpected observations can lead to revolutionary breakthroughs. Let's begin with the classical understanding that existed before 1911. Physicists believed they understood how electrical resistance behaves in metals. Metals conduct electricity because their electrons can move freely through the material. But electrons don't flow perfectly smoothly. They collide with the metal atoms, which are always vibrating. These collisions create resistance. Here's an important question. What happens when we cool a metal down to very low temperatures? The answer seems obvious. At lower temperatures, the atoms vibrate less. With less vibration, electrons should collide less often. Therefore, electrical resistance should gradually decrease. Picture this. Inside the metal, atoms vibrate and electrons try to flow through. The electrons keep bumping into the vibrating atoms, creating resistance. Based on this understanding, physicists made a clear prediction about how resistance should behave at low temperatures. The resistance should decrease smoothly and gradually as the temperature falls. There should be nothing special or sudden about this decrease. In fact, the decrease should follow a predictable mathematical relationship. Scientists expected a smooth curve that could be described by a simple equation. Even at the absolute lowest temperatures, physicists expected some small amount of resistance to remain. After all, the metal atoms never stop existing, even if they stop vibrating. In 1911, a Dutch physicist named Heike Kamerlingh Onnes decided to test this prediction. He had just mastered the technique of liquefying helium, which allowed him to reach temperatures near absolute zero. Onnes could reach temperatures as low as 4 Kelvin, which is about negative 269 degrees Celsius. This was an extraordinary achievement at the time. He chose to study mercury because it could be purified to remove impurities. Pure samples give more reliable measurements. Let me describe the experimental setup. This is crucial for understanding how scientific discoveries are made through careful measurement. The mercury sample sits in a bath of liquid helium. A thermometer measures the temperature precisely. A battery sends current through the mercury, and instruments measure the resistance. The key is to measure resistance at many different temperatures. Start warm, then slowly cool down, recording resistance values at each temperature. Precision is absolutely critical. You must measure accurately because small changes in resistance could reveal important physics. Let's imagine we're collecting data just like Onnes did. We'll record resistance values as we lower the temperature step by step. Here's what the data looks like. At 20 Kelvin, the resistance is 0.050 ohms. As we cool to 15 Kelvin, it drops to 0.038 ohms. At 10 Kelvin, it's 0.025 ohms. Everything looks normal so far. The resistance is smoothly decreasing just as predicted. Everything is following the classical prediction. The resistance decreases smoothly as temperature falls. This is exactly what the theory predicts. But now, as we continue cooling below 4.3 Kelvin, something completely unexpected is about to happen. Look at what happens. At 4.3 Kelvin, resistance is 0.008 ohms. At 4.2 Kelvin, it's 0.007. But at 4.19 Kelvin, it suddenly drops to 0.003. Then at 4.15 Kelvin, it's less than 0.0001. By 4.1 Kelvin, the resistance has completely vanished. This was absolutely shocking. The resistance didn't gradually approach zero. It suddenly collapsed to zero within a tiny temperature range. Within just a few hundredths of a degree, the resistance went from a measurable value to literally zero. Not just very small, but actually zero. No smooth classical curve can fit this behavior. This is not a gradual decrease. This is a sudden phase transition, like water freezing into ice. Let's plot this data carefully with proper units and labels. This graph will reveal the dramatic nature of the discovery. Here's the complete picture. The green curve shows the classical prediction, a smooth decrease. The yellow dots show our measurements above 4.2 Kelvin, which follow the prediction. But the red dots below 4.2 Kelvin tell a different story. The resistance suddenly collapses to zero at the critical temperature. Let me emphasize just how dramatic this collapse is. This is not a smooth transition. This is an abrupt change in the material's behavior. Within just 1/10 of a Kelvin, the resistance drops from a measurable value to literally zero. This happens over an incredibly narrow temperature range. You cannot fit this with any smooth mathematical function. This is a discontinuous jump, indicating a fundamental change in the material's quantum state. Here's a critical question that any scientist must ask. Could this be a measurement error? Maybe the instruments malfunctioned? The answer is no. Onnes repeated the experiment many times with the same result. He also found that different materials have different critical temperatures. This is real physics, not experimental error. Now comes the most important part, interpreting what this data means. What is actually happening inside the mercury at 4.2 Kelvin? This is evidence for a completely new state of matter. Just as water can be solid, liquid, or gas, metals can be normal or superconducting. Below the critical temperature, the material undergoes a phase transition. The electrons reorganize themselves into a fundamentally different quantum state. Let's explore what happens in this superconducting state. The properties are truly remarkable and defy our everyday intuition. First, there is literally zero electrical resistance. Not just very small resistance, but exactly zero. Current can flow forever without losing energy. Imagine a ring of superconducting material. If you start a current flowing in this ring, it will continue flowing forever. Scientists have observed currents lasting for years without any measurable decay. This completely violates our everyday experience. Normal wires heat up and waste energy. Superconductors do not. The current flows perfectly without any loss. The first consequence is that superconductors are perfect electrical conductors. They can carry enormous currents without generating any heat or losing any power. Imagine power lines made of superconducting material. Electricity could be transmitted across vast distances without any energy loss. This could revolutionize our electrical grid. There's a second remarkable property that was discovered later. It's called the Meissner effect, and it's just as strange as zero resistance. When a material becomes superconducting, it actively expels all magnetic fields from its interior. Magnetic field lines cannot penetrate a superconductor. Here's what happens. When you place a superconductor in a magnetic field, the field lines are forced to go around the material. The interior remains completely field-free. This property allows for magnetic levitation. A superconductor can float above a magnet because it repels the magnetic field. This has been demonstrated in countless laboratory experiments. One consequence is frictionless magnetic bearings. Because the superconductor levitates without touching anything, there's no friction. This is useful for flywheels that store energy. Another consequence is powerful electromagnets. MRI machines in hospitals use superconducting coils to generate strong, stable magnetic fields for medical imaging. Now let's discuss why superconductivity happens. The explanation requires quantum mechanics and wasn't fully understood until 1957. Normally, electrons repel each other because they're all negatively charged. This makes them scatter independently through the metal. But in superconductors below the critical temperature, something remarkable happens. Electrons form pairs called Cooper pairs, mediated by vibrations in the crystal lattice. These Cooper pairs don't move independently. They all move together in a coordinated quantum state. It's like they're dancing in perfect synchronization. Picture two electrons bound together as a Cooper pair. They move as a single unit, and all the Cooper pairs in the superconductor move in perfect harmony. Because all the pairs move together in the same quantum state, they cannot scatter off individual atoms. Scattering would require breaking this coordinated motion, which costs energy. There's an energy gap that must be overcome to break the superconducting state. Below the critical temperature, thermal energy is insufficient to break the pairs, so resistance remains exactly zero. Mercury was just the first superconductor discovered. Since then, scientists have found many other materials that superconduct. Lead becomes superconducting below 7.2 Kelvin. This is higher than Mercury's critical temperature. Niobium has a critical temperature of 9.3 Kelvin, which is even higher. It's used in particle accelerators and quantum computers. In 1986, scientists discovered high-temperature superconductors. These ceramic materials can superconduct at temperatures above 90 Kelvin, which can be achieved with liquid nitrogen instead of expensive liquid helium. The highest known critical temperature at normal pressure is about 138 Kelvin. Scientists are still searching for room temperature superconductors, which would be revolutionary. Let me conclude with important lessons that young researchers should learn from this discovery. First, precision measurements matter. Onnes wasn't looking for superconductivity. He was just measuring resistance carefully at low temperatures. But his precision revealed a completely unexpected phenomenon. Second, never ignore anomalous data. When your measurements don't match the theory, don't assume you made a mistake. Investigate carefully. The anomaly might be telling you something profound. Third, the most important discoveries are often unexpected. If Onnes had only measured what he expected to see, he would have missed superconductivity entirely. Fourth, reproducibility is essential. Onnes repeated his measurements many times with different samples. Only when results are reproducible can you be confident they're real. Fifth, technological advances enable discovery. Superconductivity could only be discovered once the technology existed to reach such low temperatures. New tools open new frontiers. Let's briefly discuss how superconductivity is used today in practical applications. Medical MRI machines rely on superconducting electromagnets to generate the strong magnetic fields needed for imaging. This has revolutionized medical diagnostics. Particle accelerators, such as the Large Hadron Collider, use superconducting magnets to guide particle beams at near light speed. This enables fundamental physics research. Quantum computers use superconducting circuits as qubits, the basic units of quantum information. This is one of the leading approaches to building practical quantum computers. Superconducting quantum interference devices, or SQUIDs, can detect incredibly weak magnetic fields. They're used in brain imaging and geophysical exploration. Magnetic levitation trains in Japan and China use superconducting magnets to levitate above the track, reducing friction and allowing speeds over 600 kilometers per hour. Finally, let's look toward the future. What are scientists working on today? The holy grail is room temperature superconductivity at normal atmospheric pressure. This would transform energy transmission, transportation, and computing. There have been recent claims of room temperature superconductivity under high pressure, but these require extremely careful verification. Remember, reproducibility is essential. We still don't fully understand the mechanism behind high temperature superconductivity. The BCS theory that explains conventional superconductors doesn't apply to these materials. Researchers are exploring new materials, new crystal structures, and even materials that don't exist in nature. Computational methods help predict which materials might superconduct. Let me summarize the key points from this scientific journey through superconductivity. We started with the classical prediction that resistance should smoothly decrease with temperature as atomic vibrations diminish. Careful experimental measurements by Onnes revealed something completely different: a sudden collapse to exactly zero resistance at a critical temperature. This dramatic discontinuity indicated a phase transition to a new quantum state of matter, where electrons form Cooper pairs that move in perfect coordination. Superconductors have two defining properties: exactly zero electrical resistance and the complete expulsion of magnetic fields from their interior. Applications of superconductivity now span from medical imaging to particle physics to the cutting edge of quantum computing technology. The search continues for materials that superconduct at higher temperatures, ideally at room temperature, which would revolutionize technology. I want to leave you with a final message that captures the spirit of scientific discovery. Measure carefully with precision. Question your assumptions. And when you encounter an anomaly that doesn't fit the theory, don't dismiss it. That anomaly might be nature trying to teach you something profound. Remember that the most important discoveries often come from unexpected places. Onnes was not searching for a new state of matter. He was simply measuring resistance. But his careful, systematic approach revealed a phenomenon that changed physics forever. Stay curious, stay rigorous in your methods, and stay open to being surprised by nature. That's how science advances.